Uh, my name is Dominique Gabiou. I work in Swiss University of Applied Sciences, and I am the coordinator of the H2020 project Domos. I know that this session is about turning buildings into active nodes. Our project is related to making building active, but it's not the central target of the project. The central target of the project is to have an integrative approach of all smart services, and more specifically smart energy services in buildings. And we aim at developing an ecosystem where we can develop such energy services, and of course flexibility or active node control of buildings is part of these smart energy services. So here you see some basic data related to our project. This is a 3-year project and year 1 is over. Okay, what do we see in today's buildings? First, we see more and more online appliances being installed in the buildings. For example, if you have a heat pump today, it has some communication interface. If you have some EV charger, same thing. Simple systems like lighting systems you can have, or even coffee machine, you can have them online. And basically the model is that a platform, some kind of IoT platform, let's name it like this, is controlled by the appliance manufacturer, and you've got some kind of application to monitor or control the appliance, but and the whole, the application, the platform, and the appliance is controlled by the appliance manufacturer. And what you see parallel silo solutions, and in the future, more parallel silo solutions are expected. For large or high-end buildings, they have an integrated building automation systems, basically installed at construction time or deep renovation time, where you have basically a wired building automation system to control heating, ventilation, and cooling typically. This means that smaller buildings do not have any building automation system, as you probably know. When we see this situation, we have two main problems that Domos wants to tackle. The first one is the lack of integration. Each silo solution has its own logic to connect, to control the systems, and the users have a relatively bad user experience because they have to deal with independent and uncoordinated management of their buildings. The second problems that occur is that sometimes you need applications that control more than one appliance. Typically, in flexibility control, you have to orchestrate PV inverters, grid operators, battery storage system, heat pump, blinds, lighting, and so on. And it's with the current silo solution, this is difficult, if not impossible. So the vision we try to develop and make concrete inside the Domos project we want to decouple the applications from the appliance models. So an appliance model, and for this, we want that application have a generic view of appliances of the same type. Same type means that for an application, I make it simple, all heat pump are seen in a similar way, can be monitored and controlled in a similar way, independently of their model. The model is the individual model type. For example, a Viessmann Vitocal heat pump, this is a model. So the vision that we try to develop is that appliances feature an interface depending on their type and not on their model. And if we succeed in doing this, the concrete consequence is that we can develop applications that are independent of appliance models. For example, we can have a heat pump control application not bound to a specific model, and also we can easily have applications spanning multiple appliances. So we want basically to develop the mediating layer between appliances and application. Excuse me. So basically, I imagine Domos as is the operating system of your laptop. On below, you can connect any hardware peripheral to your laptop, and you can connect any appliance to your house operating system, provided, of course, that it has a digital interface. On the top side of the operating system of Domos, you can connect multiple applications, and the Domos mediating layer allows a simple connection between applications and the appliance on the field in the buildings. What Domos is and what Domos is not. Domos is basically a specification. So Domos indicates how this can be done, but basically Domos does not provide a single solution to do it. So Domos is not an IoT framework or an IoT platform. This is a specification that can be implemented on any open source or commercial IoT platform. This ecosystem specification uses the IoT standards that are well known by developers, so as it's easy for stakeholders to adopt this Domos ecosystem specification. I don't want to enter into many details on how we do it. Basically, we take over IoT standards, either established or emerging. And one of the emerging standards we are basing our specification on is the Web of Things specification from V3C. V3C is the entity that makes web standards. In the Web of Things, as its name implies, there is a concept of thing, and an appliance in the Domos concept is fully compliant, is actually a VOT thing. And to make it very simple, VOT abstract anything or any appliance as a set of properties that can be read or written, a set of actions that can be that can be executed by an application, and a set of events, and application may subscribe to events and be informed on the occurrence of the events. So we model each appliance as set properties, action, and event according to VOT architecture. And basically, the appliances, we all know that they are extremely diverse, and we don't want to change the appliances, and we don't want to them to comply with some kind of new standard. The VOT just asks that each appliance is actually described in a machine-readable document called a things description. And this basically what Domos does, it applies the VOT concept to smart buildings. So here, if you have 3 appliances, which each with different protocol, what you need is you need to personalize a generic VOT library with things description, one things description per appliance. I come up later on who is preparing this things description. Domos is basically a set of guidelines on how to implement the VOT architecture in the concept of smart buildings. And also, we have, in addition to things description of individual appliances, we have another machine-readable document, which is called a building description. So this document contains metadata relating to the building. Metadata means, for example, what are the properties of the building envelope, what are the properties of the heat generation system or heat distribution system. And this building description has links to individual things description in of the appliances in the building. And the third thing, which is quite important if we want to have this interoperability, is that we give the same name to the same concept. Let's call it like this. And an important part of the project is to establish the so-called Domos ontology, which is actually the nomenclature we want to use to name concepts that are of importance in our project. A concept, this is, for example, we need to name in a unambiguous way the forward temperature at the output of the heating system, and we need some kind of generic name for it. Of course, we base our so-called ontology on existing ontology like SAREF ontology, and what is relevant for flexibility, we use the flex offer ontology to express the available flexibility and to order flexibility in buildings. It's not quite the place to speak about business, but nevertheless a few words on the business perspective. First, with Domos, we open the door for new roles. One of the new roles will be that we have IoT platforms dedicated to buildings, and we can imagine to have a role as an operator of an IT platform for buildings. This will allow building owners, if they use such platform, to have an integrated approach for building management, for energy management in buildings, and also an integrated approach for managing cybersecurity and privacy. And also we can imagine to have a new roles like application developer or smart service operator, where you can develop service without actually selling or having sold the hardware. So you can be a pure software player, let's say, for example, for energy management. Some questions are still open. For example, who will pay for this IoT platform operator? Who is responsible if the management application is independent of the manufacturer? If there is a problem, who is in charge? We need things description, so we need for each model of appliance, we need a document that describe actually how to physically communicate with such an equipment. So we need a repository for them, and we need to establish them. We need to be sure that they are still up to date. Another question is, will the appliance manufacturer be ready to play with SaaS, or will they oppose such a system? And if you have a new system like this, it's important. It is attractive if there are many appliances, models, and many applications, but many applications and many appliances will be compliant only if there is a critical mass. So the startup process is not clear up to now. One of the possibilities will be that utilities will evolve into operator of IoT platforms for buildings. That's at least what we examine now. The approach that we have by defining the system is really based on demonstrators. So we gather requirements from demonstrators. We developed technology accordingly. We implement the technology in demonstrators, and we validate the demonstrators, and possibly we make another circle if needed. And regarding demonstration site, we have 5 demonstration sites, 2 in Switzerland, 1 in the region of Paris, France, and 2 in northern region of Denmark. What kind of services do we demonstrate? So we demonstrate energy flexibility. This means concretely building become active node of an electrical grid in Sion, and we have also peak shaving for district heating in Aalborg. We have also control systems inside building with smart thermostatic valve to improve the energy efficiency of the heating generation and distribution. We have dashboards for inhabitants that tells them what is the energy situation of this building. And we have also an automated data-driven performance analysis of heating system, and we eventually want to test non-energy services. Thank you for your attention.
I don't know if Dominic still can hear us. It's nothing. So, yes. We would like to thank Dominic for the presentation. So we will proceed with the next one, which is building information aggregation, harmonization, and analytic platforms. That will be done by Dr. Stoyan Danov from the project B. So,
hello. So I hope you can see my screen now.
yes, if you can also put the presentation in presentation mode, that's great.
Is it okay?
Yes, great.
So, my name is Stoyan Danov. I'm a researcher from SIMNE, and I'm responsible for the data harmonization layer in the project, which is a work package. So just to show you some general information about the project. So it is a project started last December. Previous year in the call for big data for buildings. So the consortium consists of 12 partners. It is coordinated by Inetum, Real Domain, and from SIMNE. So it is a 36 months project. Well, the big project aims to create a big data infrastructure and to demonstrate application of big data analytics technologies for the complete building life cycle, different use cases over more than 4,000 buildings, and organized in 4 large-scale pilot test beds. The specific objectives of the project are to create an open, flexible big data reference architecture that will allow different specific implementations of architectures depending on the needs to solve these kind of problems. Another objective is to create a common open standards-based data model that will help standardize and harmonize data from different data sources, and also to create an open cloud-based analytics toolbox that could be reused and integrated with different instances of this reference architecture, and is compatible with the standard data model to provide advanced analytics. And other objective is to validate this analytic toolbox together with the reference architecture, and finally to promote the widespread adoption of this platform. So the project, as I said, is to create an analytics toolbox and to evaluate its applicability on real business cases, where these business cases should be evaluated by fulfillment of different technical, business, and also legal KPIs, and also to perform a cross-pilot validation in these scenarios by using data from combining data from different sources. And these basically there are we're evaluating 6 different business cases. So you can see here them. 3 of them are tested in Spain and 3 other in Greece. So these business cases, let's say, are broader areas of applications. In total and globe, 15 different use cases, from benchmarking, building portfolio management, energy certification, and also building life cycle, let's say, by integrating data from BIM, from other data sources, and to perform different analysis for planning, renovation of buildings, but also managing energy performance contracts, savings, optimizing comfort, and also providing flexibility services for the electricity grid. So these use cases are implemented by first standardizing the heterogeneous data streams over a common data model, aligning them, and then using them over the architecture to feed with this standardized input the analytics toolbox. So the concept of the project is really very wide. We wanted to cover, let's say, a wide scope of wide range of different services over the whole life cycle of the building. So starting from the design, construction, operation to the support refurbishment decisions, and we aim to produce considerable impact in these 4 areas you see. So building performance monitoring, also in building energy efficiency investment, electricity grid support, and also to provide tools to support policy decisions through the different use cases we are developing. And these, so as you can see, cover BIM data integration, also integration and simulation tools, rating of buildings, and also data harmonization from different sources as a step for interoperability of data. So here you can see the conceptual view of the reference architecture. So it aims to provide possibility to acquire data from different sources, to exchange these data from different sources, and to harmonize these data over the common data model, which is standard-based, and then to enable the use of these data for different analytics toolboxes that could be like implemented in a containerized way, so that they could be reused in different applications over different type of storages, combining local storage and also cloud storage, and just to provide flexibility in the implementation. Also, their important part is the security layer, which is to control the different data exchanges in terms of compliance with the GDPR, but also analyzing risks and also applying advanced data access management. So the important, I think the primary concept in the project is the the data standardization. First, because this is the main challenge in the interoperabilities of data, and is the in the building sector is that that there is no single standard or ontology covers the whole scope of possible use cases in the building sector. So we have different standards, but they also have some deficiencies. So, for example, SAREF covers more IoT applications, and BIM covers static data. But when you want to combine these data, for example, to assess in the context of evaluating the effect of energy investments, where you need to combine monitoring with building characteristics. There is no standards that sufficiently complies, and also our use cases use also data from cadastre and different other data sources, which are not covered by a single standard. So the aim of the work package harmonization is to create a big ontology which is standards based. So take pieces from different existing ontologies, but at the end to contribute also to the further development and align this model to the different standards. So in this way to enable interoperability of data. So as we're now in the first year of the project, we already created the first initial data model and ontology of PIC, so which consists of description of different concepts, attributes, and also developed an extensive number of taxonomies that will support, and also developed a data model in UML, which describes also captures the relations of this. Now we are in a moment of validating of this model and mapping the initial the old data sources over it in order to make them usable for the analytics toolbox. So this is the direction of the project. So we see our intention is to contribute substantially to the standardization of the European buildings data by aligning them over a common open data model, which will be published, will be also aligned to the main mapped and aligned to the main standards. This also will be published as an open information. Will be a significant output from the project. We will demonstrate the interoperability of data between different data hubs in national and supranational level. We can expect creation of new data-driven business models and opportunities to innovate in energy services. As I said, we cover 15 different use cases that rely on different data sets. So we also expect to engage key stakeholders in gathering data for building databases that will contribute with real data. For example, one of the use cases is to gather information on energy efficiency investment and their real impact. So to contribute for example, to the DEEP, the Risking Energy Efficiency Platform at European level, but also to assess the effect of these investments with empirical data. We also want to help to integrate relevant digital technologies in the building sector and to help with this flexible and reusable reference architecture to be integrated efficiently into different value chains. So we're going to prescribe solutions, but not will allow sufficient flexibility for the users to reuse different parts of the architecture and the analytic modules and to adapt them to their business needs. And finally, we over this common and harmonized data model will want to help to emerge around sustainable ecosystems of different big data platforms. So in this sense, we are very interested in collaborating with other projects and platforms, providers and stakeholders from the building sector that to promote together this common data model, so which is now in its first stage, but it will be continuously further developed by integrating more data and aligning it to more standards as the needs develop, and to jointly promote it as a base for data interoperability in the building sector. So, and also want to provide these advanced analytics modules in a way that is completely reusable and independent on the local, let's say, operating system or system constraints of the building. So that's it on my side. We're open to contact me and to discuss this, me and the project coordinators.
Thank you very much, Stoyan, for the presentation. Very elaborated, I have to say. Yes, at the end, when we have the roundtable, maybe some questions that have been raised will be answered at the end. Thank you very much.
Thank you.
Now we should proceed with the next presentation, which is on sparse data and prototypes, data-driven energy management with the presence of novel technologies. That the presenter will be Brida Buvik from the RES4Build project. So, Brida, if you can share your screen, the floor is all yours. Great.
Okay.
Let's see. Thank you.
Okay. Can you also hear me?
Yes, loud and clear.
Okay. Thank you. Good morning, everyone. So my name is Brida. I am a researcher at the Flemish Institute of Technology in Belgium, in collaboration also with Energyville, which is a research institute here in Belgium. This presentation, I will present part of the work that we at Vito we have done in the context of RES4Build. So the presentation will have 4 main parts. So first, I will give a brief summary about the RES4Build project. And since we are focusing on buildings, I will discuss a bit more on the building modeling approaches and then focus on the Greybox modeling, which is what we have used quite a lot in RES4Build, and then discuss some future opportunities. So RES4Build is a project that is aiming at renewable energy-based solutions for decarbonizing energy use in buildings. The project started in 2019 and is running for a period of 4 years with 15 partners from all over Europe. So the goal in REST for Build is to develop solutions that are specifically for heating, cooling, and energy storage. So with this, we are developing different types of appliances, such as the multi-source heat pumps, PV thermal collectors, then borehole thermal energy storage systems. And together we are looking also at building energy management systems such that we can exploit flexibility from the buildings that are existing. So all the solutions that are developed in REST for Build are going to be tested in different buildings that are found in different locations in Europe. So we have a pilot here in Belgium, in Greece, and also in Denmark. That way we can explore the different weather conditions that there are here in Europe. So basically to buildings have some inherent flexibility that we can use in demand response applications. And this flexibility is coming mainly from the thermal mass of the building. But then to be able to exploit this flexibility, we need to model the behavior of these buildings. And by modeling, we want to see how much extra heat that these buildings can store or how much reductions in heating or cooling power that we can gain from by controlling these buildings while ensuring the comfort of the occupants or the people using the building. So there are three main modeling approaches that have been used to model the thermal behavior of buildings. We have on one hand the white box models that require a detailed physical description of the building. So by this, then we require expert knowledge on the building parameters and the properties, which makes developing of these white box models quite expensive. And then on the other extreme, we have black box models, which are purely data-driven, where the behavior of the building is learned from measured time series from the buildings. But these become less performant in the cases where we encounter scenarios that have not been captured by the data that was collected from the buildings. So in between these two, we have Greybox models that exploit the physical knowledge about the building to define the structure of the model, and then we use data to identify the parameters of this model. The main advantage of this Greybox model is that they do not require as much amount of data as the black box models, and also they do not require a detailed physical description of the building. So this makes them very flexible and scalable and can be easily used across different types of buildings. So in REST for Build, we have focused on Greybox modeling to be able to characterize the thermal behavior of different buildings. And specifically, we have looked at RC models. So RC models are types of Greybox model that group and represent the building components as thermal capacitances and resistances. So we can see this if we try to look at it with an to compare this with an electrical circuit. We could look at the temperature in the building as the voltage drops across the different nodes, and then we have the heat flux from the heat sources in the buildings as the current that we have flowing in an electrical circuit. So the thermal behavior of a building is affected by three main parameters. So we have the solar irradiation, which is the radiative component of the building environment. We have the outdoor temperatures and the heating power that we get from all the heat sources that are found within the building. So here, there's one of a very simple example of an RC model is is one where the thermal capacity of the building is summarized by one parameter, and the heat losses in the building are also summarized by a single heat transfer coefficient. So in this case, we can have the heat losses that are through the ventilation that is found in this building. And we have a single temperature node, which is the indoor temperatures of the buildings. So all the heat that is supplied in the building is assumed to go to change the temperatures, the indoor temperatures of the building. Then we can have a more complex RC model where we consider all the heat transfer not only to change the indoor air temperatures, but we also consider that the heat is also transferred to the internal objects in the buildings, such as the furniture, or also heat transfer to the walls in the buildings. And we also include like the heat losses through the ventilation. So the RC model can be very simple, where we have only one resistance and one capacitor, or it can be very complex. So when we look at the Greybox modeling process, the goal, as I mentioned before, that the RC models, they have a model structure with some parameters, and then we use data that has been collected from the building to identify these model parameters. So when we have some data set from a building, we want to find an RC model structure that best describes this data set. So we want a model that would accurately predict the behavior of the building, but a model that also has a very low complexity, because we are avoiding the complex nature of white box models in this case. But the problem here is that we still need data to be able to identify the model parameters. And in REST for Build, we have these pilot buildings and these prototype devices that we do not have historical data from which we can develop these models. So what we have done is that we have physics-based models that have been developed because we know the buildings and we know the devices. And then we use this to generate the data that we require. But of course, this is representative of the building, but we know that user behavior can always change. So once we get real measurement data from these buildings, we are going to recalibrate the models that we have and do a new parameter estimation, such that we have models that are more representative of the buildings that we are working with. So to identify the best RC model structure that describes a particular data set, we have three main steps that we consider. So first, we need the measurement data from the buildings. And this data includes the outdoor temperatures, the solar irradiation, the indoor temperatures in the building, and also the amount of heating or cooling power that has been used within this building. Then we select a set of RC model structures. So in this case, we have used 5 RC model structures from which we are going to then define an optimization problem that would help us to select an appropriate model structure for the building. So the optimization problem aims at minimizing the error between the measurement data that we have from the buildings and the indoor temperature estimates from the Greybox model that we are considering. So what happens is that when we have this measurement data, we divide it into a training and a validation data set. The training data set is used in the optimization to identify and estimate the model parameters, and then the model is being validated for its accuracy. It's being evaluated to validate this based on its accuracy with the validation data set. And from this, when we have all this information from all the different 5 model architectures, then we choose the model that gives us the lowest root mean squared error, for example. So one example of what we have done with the data that we generated for the pilots in Greece. So we considered different model architectures, starting from the simplest one, which is the 1R1C model, onto a 3R3C model, which is a bit more complex. And we found, based on the results, that the 3R3C model was much more representative of the data that we were able to generate from the Greybox models. So these Greybox models, how can they be used? There are different applications that we can consider when in the context of building. So for example, we can have Greybox models that are used in model predictive control. An example could be for minimizing electricity costs within a building. So we can steer the building to consume more when electricity prices are low. So in this regard, we define an optimization problem that is based on reducing the electricity consumption and cost in the building that is subject then to the model dynamics of the building. In this case, the Greybox model structure that we have identified. And then also we consider the comfort constraints of the users. And here we can see that by using this Greybox model, when electricity prices are low, we can heat up the building. And when electricity prices are high, we do not heat up the building. So we exploit the flexibility that is coming from the thermal mass of the building to be able to store heat in the building and release this when electricity prices are high. And we can see this here, that we are still able to keep the indoor temperatures within the boundaries that have been set by the building users. So for the future opportunities on what is next, one thing could be that we switch completely to data-driven energy management systems. But then even if we just switch completely to this, we still have the problem of the data privacy concerns, because most users, they are always keen on what is being done with their data. So this is an open question and something that I think there's still a lot of work being done in this direction. Then also when we have all this new technology that we develop, we need to test them, we need to see how they work. But then most users also, they don't want to allow their buildings to be used as test buildings, especially in the early phases of these devices. So in Rest4Build, we are also considering this hardware in the loop testing, where we have a prototype device like the heat pump, which we have the actual device, but then for the test we use a virtual building, which is a white box building model that tries to simulate as much as possible how the building is going to react to the different control inputs that it is receiving. So this is also something that we are working on, and now we are going to start with the pilots by the beginning of next year. So we are looking forward to have some very good results. Yeah. So thank you very much for your attention.
Sorry, I was muted. Thank you very much for the presentation. Thank you very much, Frida. Let's proceed with the next presentation, which is a big data application for energy efficiency in building sector. The presenter will be Dr. Zoe Milona from Matrix project. So, good morning, Zoe.
Good morning. I hope you can see my screen and you can hear me.
Yes, everything's great. Thank you.
Okay. Good morning, everyone. My name is Zoe Milona, and I'm representing the Matrix project today. I'm a researcher at Holistic, a Greek consultancy firm in the field of digital services and energy, environmental policy and planning. In Matrix, we are on one of the technical partners and service providers, and my presentation will be about big data applications for the energy efficiency in building sector. Buildings are now required to be highly efficient, dynamic, healthy, flexible, adaptable, but durable as well, and interconnected and digital, while minimizing the cost and their carbon footprint during the whole life cycle. The CO2 reduction as opposed to the Paris Agreement requires fundamental and rapid and large-scale transformation in the buildings. And the majority of the EU countries have started implementing activities towards decarbonization, but the speed of the decarbonization depends on the availability of mature technologies and the ability to supply, to scale supply chains. With the use of big data and advanced analytics, systems will become more connected and operators will have a better understanding of both supply and demand in real time. The number of connected Internet of Things devices, integrating, of course, artificial intelligence, is forecast to grow up to 70% until 2025. And in this way, consumers will become active elements of the energy systems, and we are moving from a supplier-centric model to a more consumer-centric model, enabling in this way the decentralization we need to achieve. And this is obvious also by the increase of the renewable energy sources and the alternative fuels in the energy mix. However, public participation should be significant and from consumers to become prosumers with pros and active role in the energy sector and of course in the building sector. And therefore, intelligent energy management in buildings is out of great importance. The building sector, as you know, is a unique and heterogeneous sector with big data availability from different consumption variables to act as an important asset for decision making and, of course, with valuable insights. And this is where Matrix comes. Matrix proposed solutions and vision to turn buildings into digital enhanced edge hubs with the ultimate scope to ensure sustainability and resilience along the whole building life cycle. Taking into account the high volume of asynchronous data, the challenge of non-interoperability and heterogeneity and the inefficient data management methodologies, Matrix supports the transformation of buildings into smart, energy-aware buildings towards the real data economy we like to have. The title of the project is Modular Big Data Applications for Holistic Energy Services in Buildings, funded under Horizon 2020. It's a 3-year project and started 1 year ago. Engineering is our project coordinator, and the consortium is composed by 18 partners, as you can see in the bottom of the slide. The 18 partners are from 10 European countries. Matrix consortium, I think, is well balanced in terms of company types, expertise in the building value chain, and of course in geographical distribution. We have leading organizations from the field of research, public bodies, NGOs, large enterprises, and SMEs. Moving deeper in the project, Matrix is planning to deliver a reference architecture for the building data, covering the need of the building value chain based on 3 technical layers. The Matrix governance for data collection, semantic annotation, and distributed storage. The processing layer for machine learning and deep learning models, so more oriented to AI topics, and analysis for providing a toolbox as a service. Matrix will be demonstrated in 11 large-scale pilot groups in 4 categories: performance, design, policy, and fund. And I will talk in more detail in the next slides for these 4 groups. And we have also side activities such as Big Data Alliance, standardization activities, hackathon, and workshops to understand and build a robust use of the Matrix outcomes, not only during the project, but also beyond. A few more things about the matrix architecture. It will be an AI-powered framework for decision support models, data analytics, and visualization in real-life applications. On top of infrastructure asset components, external data hubs, and data set already existing, we will develop the matrix governance, the middleware to act as a mediator between data users and data providers, including all the processing activities such as data cleansing, curation, anonymization, etc. On top of that, there will be the matrix processing layer, which encapsulates the intelligence components of the solution, providing a library of reusable AI-based machine learning and deep learning models. And finally, under the matrix analytics layer, there will be a toolbox that can be used in different forms. A visualization and reports engine for the visual representation of the stored data and the results produced from the analytical components. Analytics building services exploited through the large-scale pilots. Digital building twins as a digital representation of the physical systems of the buildings. A virtual workbench to let developers and potential innovators design and develop new services for the building sector. And as an open source sandbox in a container-based workflows that could be flexibly deployed over cloud infrastructure. Going deeper to the matrix large-scale pilots, there are 11, two test beds as well, and one digital building twin covering 9 EU countries. The first category is the performance, focusing on the improving of energy performance of buildings with predictive capabilities for energy demand. Next, we have the design group of large-scale pilots for retrofitting action, refurbishment, and development of the building infrastructure. The policy group of LSPs focuses on supporting policy making and impact assessment at local and EU level. And finally, a fund group aims at enhancing reliability and risk reduction on energy efficiency investments for buildings. So these are the 11 large-scale pilots located in different countries and covering a large geographical coverage and different socioeconomic backgrounds as well. Each category has minimum 2 large-scale pilots, and all of them represent the whole building value chain. Covering also the whole building life cycle as well, from the product manufacturing to the operation and maintenance, along with cross-cutting fields such as policy research. The large-scale pilots come from different perspectives and scales also, for example, building as an individual element, so in building level, and the aggregation at various scales. And through Matrix, we're moving from the district level as well to national and EU level. One of the main assets of Matrix is the building analytics services that are going to be developed. They are now in the development phase, but soon the first version of them will be available in the end of October. They are 12 in total and are referring to each large-scale pilot group. For performance, we have energy prediction, building automation and control, KPIs calculation, technical building management and optimization for network operation. Regarding the design, we have technology catalogs and energy conservative measures-based scenarios evaluation. The policy group will be covered by CCAPs, decision-making support, EPC harmonization and compliance with policy assessment services. And finally, measurement and verification of energy saving service and energy efficiency refurbishment financing service will be prepared for the fund group. The next 2 slides will present services from the performance group in more detail. These are 2 of the services that Holistic is responsible for. They are under development, as I said, but they will be ready at the end of October, and I will present some initial results today. So the first one is the energy prediction. And it's used not only for prediction and monitoring purposes, but for maintenance purposes as well. In Matrix, this service refers to an energy community, which uses several PV plants for energy production. The service energy prediction offers predictions capabilities for short-term forecasting with the use of optimized and validated machine learning and deep learning models. The added value is also that this can be used via transfer learning techniques to forecasting PV plants production in other locations rather than this the demonstrator energy community. On top of that, and the monitoring of the PV performance, maintenance capabilities are also foreseen by identifying possible malfunctions in the PV plants. In this slide, one more case from performance category and energy prediction service along with building automation and control is presented. The service allows the prediction of building energy in total and of course the subsystems of the building such as lighting, heating, cooling, ventilation, and depending on the building type, refrigeration as well. This enables the building energy analysis and the monitoring in real time and of course the forecasting of the energy demand. Specific energy efficiency indicators are used for monitoring different zones of the building, which set the base for system diagnostics with fault detection, controls optimization, and energy efficiency action plans analysis for reducing energy demand, but maintaining as well the interior quality in the zones of the buildings. All the large-scale pilots, categories and services target to a very wide range of stakeholders. These are the building value chain stakeholders, IT industry players and SMEs, industry association and technology clusters, research and academia and policy makers, and of course standardization organizations. And my final slide is about the Matrix Big Data Alliance, which officially kicked off a few days ago. This alliance is a structured collaborative space for selected and active stakeholders that together will try to solve the practical challenges of relating to building lifecycle management using big data and by combining meaningful data sets and using the data analytics. Our scope through this is the engagement and the interaction of the organizations and the facilitation of a common workflow for a cyclical stakeholders process, let's say, to connect and utilize open data sets. So if you have data sets on buildings or energy systems to analyze, if you are a data analyst who can help others to make sense of their data, or a decision maker and buildings professional who needs better data and information, you're invited to join this allowance and work together to this direction. And I think this is all for Matrix and how we're planning to help towards the transformation of buildings into active nodes in the future energy systems. For more information, visit us on the website and follow us to keep up to date for our activities. Thank you very much.
Thank you very much for the presentation on Matrix. Thank you. We should continue with the next presentation of the workshop, which is shaping trustful digital pathways for the integration of the building data value chain and the realization of advanced data sharing-driven energy services. That will be done by Tassos Tsitsanis, which is the Business Innovation Manager from Beyond Project. So, Tassos.
Hello, Lenny. Hope you can see me, you can hear me, you can see my screen in presentation mode.
Yes, maybe you can change it because you have two monitors. Yes, that's great. Thank you, Doctor.
Okay, that's good. So, thanks a lot for the introduction. I'm Tassos Tsitsanis. I'm the Business Development Director of Suite 5 and the Business Innovation Manager, as Eleni introduced me, in Beyond. First of all, I would like to thank you for participating in our workshop. It's a real pleasure and a great opportunity to exchange knowledge and experiences out of our projects. So I would like also to step on the previous presentation made by Zoe, since there is some relation between our projects and at least the introductory part, and with regards to the different dimensions, the different Ds of an energy system, since our focus in this workshop actually is to evaluate and assess and discuss actually how the data and the intelligence that's coming from the buildings and extracted from the data that they produce can be utilized, let's say, in a wider context and as part of the future energy system integration. But before going to the details, I will start with a brief overview of our project. Beyond is a project that is funded under the topic B46, referring to big data for buildings. It is a sister project to Big Data Matrix that were presented prior to this slot. The project started in the 1st of December 2020. The consortium involves 13 partners from 8 countries. We have 4 demonstration sites involving a variety of actors from the building and energy data value chains. And as the acronym of the project highlights, we are a project that does not focus only on the buildings, on introducing intelligence in the operation of the buildings and optimizing whatever has to do with the internals of the buildings across the life cycle, but we are going even beyond in order to introduce buildings as active nodes, as we say, and active stakeholders in the overall and future energy system. So, as mentioned before, I will start from the different Ds of the energy systems in order to a little bit explain our motivation around Beyond and why we introduce our approach that will be explained later around big data for buildings. So definitely we have the decarbonization goals that are set for the future energy system. These goals are becoming continuously even more ambitious. Actually, to tell you the truth, when we started with the proposal of this project, we had less ambitious targets than the ones that have been set right now with the Fit for 55 package that has been recently released. So whatever we develop and whatever all the other sister projects are developing, let's say, is becoming a necessity, and we need to be even more ambitious ourselves with regards to the impact that we want to achieve. And considering these decarbonization goals, it is a natural consequence and an expected pathway, actually, that the energy system will become even more decentralized in the future in order to accommodate additional renewables, but also new assets that are introduced in the overall picture, like storage and batteries, electric vehicles, IoT devices that can smarten the operation of a building or another facility. And apart from the positive things that decentralization can bring, actually we have some challenges to address, since by decentralizing the energy system and introducing such a variety of facets to the different edges of the system, it becomes imperative that we have a fundamental transformation in the control routines of the energy system. So centralized control is not anymore a reality or something that we could rely on. The control is transferred at the edge of the system, at the different endpoints and the different devices and different systems that reside at the edge of the system, and increase significantly the complexity of control and call for an increased coordination between the different actors involved in ensuring the overall reliability and security of supply of the energy system and the overall performance efficiency, if we can call it like this. And this coordination needs to be collective, first of all. It needs to involve all different actors in order to all together contribute to the optimization of the energy system, but at the same time and simultaneously achieve their individual goals for optimizing the performance of their assets, and in our case, of their buildings. The decentralization, of course, the introduction of the new assets in energy systems and the continuous penetration of such assets comes together with the digitalization part. Since all new assets, let's say, are able to generate data, to generate huge volumes of data, if we consider them all together at varying formats, at varying granularities, at varying volumes. And actually, apart from the fact that they generate data, they introduce also some new variables in the operation of the system, which are either stochastic, like in the case of renewables, and introduce a significant uncertainty in the overall control optimization of the system. While in other cases, when we have to deal with new devices, with electric vehicles that are not yet considered in relevant models that represent the operation of the system, in some cases, we are not dealing only with stochastic data, but with data that completely transform, completely alter actually the predictability variables for the different parameters that need to be monitored and optimized across the system and across the value chain. So, given all these parameters and all these challenges that are introduced by the decentralization and the digitalization aspects of the future energy system, we understand that we are dealing with a system with a complexity, with an increased complexity. And this requires, as I said before, the coordination between different actors, the data exchange actually between different actors in a trustful and transparent format in order to move from data silos to a complete ecosystem, an integrated ecosystem of data sharing, knowledge sharing, and coordinated control of the variety of assets involved. And this calls for the creation of a collective intelligence framework that is created by this value chain integration. And to give you a visual of what we need to address as part of the future energy system, and this is, to tell you the truth, a simplified view of the interactions and the data exchanges that happen between the sample and the portion of the actors involved in this future setup. We can see that buildings are naturally placed at the center of this complex diagram, since they are considered, let's say, as a key actor for the digital energy transition, and thus the key data source for optimizing resources at different sides of the energy system. So we can very easily view in this and understand out of this figure that buildings can be the source of data for network operators, for example, not only for optimizing their networks by analyzing and forecasting demand generation aspects, but also by analyzing the flexibility that can be provided by the different assets residing on the demand side and within buildings. But they can also can also utilize such data streams and such data analytics in order to optimize their planning processes and as such optimally size new components that need to be introduced in the energy system in order to ensure security of supply and stable operation, while optimizing their investments in order to accommodate such new DERs added to the system. In the same sense, new actors like aggregators are in need of this data in order to better place themselves in flexibility markets and flexibility transactions with network operators at both sides of the network for the provision of either ancillary or balancing services. And apart from these typical actors, we have also a strong reliance of city authorities in such kind of data in order to facilitate their urban planning capabilities, to improve their urban planning capabilities, and facilitate informed decision making. ESCOs are also a very tightly linked partners with buildings, since the knowledge that can be provided out of this data and the different assets involved in building can facilitate evidence-based renovation planning, but also optimize real-time control of building assets in order to achieve increased rates of self-consumption. On the other hand, since the retailers actually, the role in the energy market is continuously evolving and increased, it is really important, let's say, to somehow move away from the traditional data types that they are currently utilizing, they are currently sharing and receiving from network operators in order to allow them to receive more granular and real-time data, not every 30 days or 2 months, but actually in real time in order to facilitate the provision of new services, new innovative services, and transform themselves to a service provider rather than a commodity provider. And on the other hand, better position themselves in energy markets, avoid imbalances, achieve the effective realization of their energy efficiency obligations, and on the other hand, be able, let's say, to provide additional services that are not placed in the energy spectrum and can refer to non-energy services for comfort preservation, for security, and so on. So in this ecosystem, we can see that we do have a lot of data interactions that need to be facilitated and actually make the data generated by buildings and currently kept and analyzed in silos, which is, okay, something valuable for the buildings themselves, but we need to make this data reachable and available to other stakeholders that their operations are directly or indirectly affected by the data and the assets that operate within the boundaries of specific buildings. In this sense, we are introducing two main blocks of developments and two main technological blocks in our project that refer, first of all, to the realization of a big data platform, of a reference big data platform, that will allow the collection, the transformation, the mapping, the curation, and the overall management of the data that are available on the building side. And on the other hand, we are developing an analytics toolkit, which is not something that will be a black box, a completely black box for the receivers of the service, for the users of this kind of service, but it will allow also stakeholders involved in the energy and building data value chain, not only from the building side, but also on the retailer, on the utility side, to develop, to create their own models, create their own pipelines of analytics, their own workflows, execute them, and receive results based upon their needs by involving in this kind of activities their data scientists, their data science teams and units, in order not to rely only on pre-trained analytics that are provided by our project, but also have the opportunity to develop themselves in a transparent and useful and usable manner the analytics that they want to perform in order to optimize their operations, not only in the frame of the applications that we offer in the project, but also beyond these boundaries. As part all these two main building blocks actually of our project are complemented by a data sharing framework, a transparent, a trustful data sharing framework that will allow the secure and trustful data exchange utilizing DLT technologies, distributed ledger technologies, and in order to create an economy around the data that are produced by the buildings. Actually, as part of the initial activities of our projects, we have identified that, first of all, building owners cannot realize the data, the value that is hidden behind their data, and not only the value in operational terms, but also the value in monetary terms. And they could evaluate it as a strong motivation in order to share their data, of course, by choosing with which they will share this data, and making them available and getting remunerated for sharing them by other stakeholders. So by utilizing these tools, these building blocks, we are providing a complete service bundle to data and intelligence provider in order to properly treat, to properly manage their data, first of all, to ensure the sovereignty of their data by defining on their own and according to their preferences specific data access policies, deciding if their data will be encrypted, will be shared in encrypted format or not, and under what license they will be shared, and define also anonymization, the anonymization level of their data by jointly assessing anonymization, the functions for anonymizing their data and the utility that can be achieved out of the anonymized datasets. Apart from this, we involve in the overall picture and we provide services for the data consumer in order to be able to search upon specific datasets that are being made available to our platform and are shared by the data producers, then receive not only data but also intelligence, because data analytics in our case is not just a result, but it's a tradable commodity as well, since it will become a derivative data asset that will be shareable through our data sharing service bundle. And in this way, receive the information that is really useful to them based on the data coming from the buildings in order to introduce them subsequently into a series of applications that reflect and can effectively address and tackle their operational challenges. In technical terms, we introduce, as I said before, a series of bundles for effortless data management, first of all, in order to enable the curation of the data utilizing machine learning concepts for data quality enhancement, the mapping of data coming from heterogeneous sources and devices into our common information model, utilizing standardized notations of existing, typical notations actually, of existing standards, and properly mapping them into a common structure that we have developed and we will continuously update and manage throughout our project in an effective way and in an effortless manner. And on the other hand, we introduce advanced search and querying service bundles in order to support data consumers in finding the data that they are really looking for, perform an intelligent matchmaking based on the profiles and based on the type of the organization, the type of data consumer that is involved in the overall Beyond ecosystem. And on the other hand, apart from data, we provide access also to analytics results, but as I said before, they are becoming tradable commodities in our framework. There is the bundle for the analytics services as well. As I explained before, the platform integrates a comprehensive analytics toolkit that does not only executes analytics, but also facilitates the design of analytics pipelines to be later on executed in our execution engines. And the types of analytics that we will, as a project, offer through the platform in the form of pre-trained analytics and alternative implementation of such pre-trained analytics in order to address and be easily adaptable to different contexts, different data granularities, and different data availability, refer to personal analytics, mainly focusing on energy behavior analytics, comfort analytics, and personalized flexibility analytics, along with industrial analytics that take the abstraction of analysis at an upward level in order to deliver aggregated demand forecasts, generation forecasts, flexibility analytics, and so on, and facilitate planning purposes of external stakeholders. These analytics, of course, are complemented, are generated, let's say, through the deployment of the respective analytics execution engines, both in the cloud and also at the edge in case this is required. And we also have to address confidentiality issues with our data owners. Interoperability, as I mentioned before, is safeguarded by the common information model, the common structure that we have delivered through our project in order to be able to map different concepts existing in the datasets of data owners to the concepts that we have modeled in our common information model. And on the other hand, as I said before, and I mentioned before, we are focusing a lot on sovereignty, since we consider it as a key challenge that we need to address in order to facilitate engagement of building stakeholders, engagement of building occupants in the overall data sharing ecosystem that we are promoting through Beyond. And in this sovereignty framework, let's say we are introducing end-to-end data security mechanisms, mainly focusing on encryption and data privacy mechanisms that will allow stakeholders, data owners, actually themselves to define the anonymization that they want to apply over the data, and the access policies that they want to introduce in order to define in very detail with what type of organizations they want to share their data, with what type of data consumers, to be more specific, with along with other parameters like the country and other criteria that they might apply and filters that they might apply in order to fine-tune the access policies that they want to apply over their data. In security terms, we also provide an on-premise environment and secure experimentation ground in order to address cases that data are not allowed to leave the premises of building stakeholders, so as to enable the realization of our services at the local level, at the on-premise level, and the execution of relevant analytics at the local level. And moreover, we enhance this secure experimentation with playground and the overall analytics execution with secure multi-party computations that allow for the execution of local analytics by utilizing data coming from other on-premise environments. And all these are complemented by the data sharing mechanisms that are stepping on data contracts that are signed between data consumers and data and data providers, and reflect also the economic terms of these data exchanges performed between them. On the energy side, and on top of our data-relevant developments, we provide a bundle of applications and a bundle of data-driven and data-sharing-driven, actually, energy services, addressing the needs of different types of stakeholders included in the value chain. So we are providing applications based on digital twins and the enhancement of digital twins to accommodate even more advanced forecasts and analytics for data-driven urban planning. For city authorities, we provide applications for the informed and the evidence-based planning of energy infrastructures and the sizing of relevant investments for network operators, either on the electricity side or in the district heating side, since we are involving both types of operators in our consortium and in our demonstration activities. On the planning side, we are focusing also on introducing more detailed and fine-grained analytics results with regards to occupants' comfort, with regards to forecasted energy behaviors on digital twins for advanced renovation support and optimized planning of renovation projects in order to safeguard also the security in the investments that are performed in the form of energy performance contracts and reduce the gap between the predicted and the actual energy performance of buildings. And we complement the planning, the digital twin-based planning with additional services referring to the actual operation of the buildings for optimizing in real-time energy management, for performing a comprehensive and analytics-based asset management for predictive maintenance of specific assets residing in the buildings, and especially HVAC devices, and maximizing self-consumption at the building level in the case that we accommodate demand together with generation and storage. On the retailer side, we provide a bottom-up portfolio analytics service in order to optimize the performance of, to better understand actually the performance of their portfolio and experiment with new concepts for dynamic energy pricing. And on the prosumer side, we provide a personalized analytics and automation service in order to make it even more easy and even more fancy, let's say, to get involved in overlay transactions for flexibility with aggregators and participate in dynamic pricing schemes with energy retailers. Nevertheless, this is complemented by non-energy services, as I mentioned before, with regards to comfort preservation and security. So whatever happens in automated manner is happening, let's say, in a way that properly balances energy performance with the comfort of occupants within a given building. So I will not spend much more time, let's say, on the part of the applications that we are providing. What I want to highlight is that all these applications are data consumers in our framework. So all of these applications are involved, let's say, in data contracts with data owners in order to utilize data, in order to utilize derivative data in the form of analytics and introduce them into their optimization functions to deliver the services that we envisage. The demonstration of our technologies will be performed, let's say, as I said before, in 4 demo sites involving retailers, DSOs, aggregators, district heating network operators, city agencies, and building managers in Greece, Spain, Finland, and Serbia. And as a last statement in my presentation, since I think that I spent much more time than what was expected, we are currently finalizing the architecture design of our framework, of our technologies and our solutions. But in parallel, we have commenced a rapid prototyping process, which is expected to deliver a beta version of our platform and our analytics services in the next 4 to 5 months. This platform will be openly accessible not only by the consortium, but also by external stakeholders. So at a certain time, and given the collaboration that we have with other projects and sister projects, we will invite you also to join our platform, experiment by uploading your datasets, by utilizing the analytics functions of our platform, and become, let's say, early adopters and early testers also of what we envisage to deliver through Beyond. So this will be something that we will be following up with you in the next months in order to keep you engaged and hopefully enable also some kind of data exchanges between our platforms, utilizing the data contracts that and the data sharing approach that we are introducing in Beyond. So thanks a lot. Hopefully we'll have more to discuss in the roundtable session.
Thank you, Tasos. Thank you very much for the presentation. Of course, we'll have a lot to talk after all the presentation finishes on the open discussion. So please, if you want, on the Q&A session, if you want to post any question in order to address them at the open discussion. So at this moment, we should continue then with the next presentation, which is Enhanced Energy Flexibility Forecast through the Merlon IoT-ready solutions. The presenter is Angelina Kataraki from
Hi, thank you, Eleni. Thank you for that. Please confirm that you can actually see my screen in a presenter's mode.
At the moment, no, but we'll just give it a minute. Okay, yes, now it's perfect. Thank you.
Okay, thank you for that. So good morning, everybody. My name is Angelina Katsfaraki. Today I will be representing the Merlon project and Hypertech. Beginning my presentation, I would just like to give you a rough idea what is Merlon about. Our project is actually introducing an integrated modular local energy management framework, and it aims to the holistic operational optimization of local energy systems. Our consortium consists of 13 project partners, and our Hypertech team is overtaking the role of the coordinator in this project. Feel free to visit our social media channels included in this slide. In order to stay within time, I will go quickly through the presentation of the project itself. So to give a quick introduction in the technologies included in the Merlon project, as Merlon aims to contribute to the energy transition overall, it tries to define effective business models with focus to energy communities, and also introduce and integrate an ICT framework which steps on interoperable solutions in a human-centric manner. So what does that mean? First of all, Merlon is utilizing human-centric automation, trying to always respect and preserve the user comfort when it comes to implementing automation actions on site for both commercial and residential buildings. It steps on an IoT infrastructure, meaning that it utilizes off-the-shelf devices that allow to extract information in relation to the indoor air conditions and energy consumption of residential and commercial spaces in order to extract context-aware flexibility for the participation in DR programs. It considers distributed intelligence, meaning that it has the optimization of the project has multiple levels and different and considers different local generation levels as well, such as flexibility provision to integrate the maximum amount of renewable energies and avoid curtailment in the network, also allow the general user satisfaction. It also allows the integration of base systems. And finally, in its business models, Merlon considers both the aggregators and the DSOs. So there are two basic, there are two pilot sites in the project, and this is the village of Strem in Austria and also the Crevillent area in Spain. The basic drivers and challenges that inspire the Merlon solutions are, first of all, the constant and rapid increase of distributed PV plants and other volatile power generation methods, then the increasing popularity of electric vehicles, and that leads to an increased number of charging points. The demand of the prosumers to be empowered within the energy markets, issues that arise with voltage in the distribution grid from incorporating a lot of renewable energy, high shares of renewable energy, and the fact that the maximum capacity of renewables in the grid is almost reached. So looking at the Merlon solution, you can see at this point that there are a lot of stakeholders involved. We're considering the distribution grid and the aggregator and different levels, like the DSO, and different levels of cogeneration and renewable energy production. But as this presentation's title suggests, we are going to focus to the local flexibility. So what is the local flexibility? In our perception, this part focuses mainly on households and prosumers, such as small commercial buildings, office spaces, etc. And it employs a building flexibility manager in order to extract context-aware flexibility. This is taking into account information on PV generation, heating in the sense of space heating and domestic hot water, cooling, lights, and storage. And it tries to extract flexibility, personalized flexibility based on, first of all, virtual energy storage considerations, on flexibility, on comfort profiles of the users, and allow the implementation of tools that allow the monitoring and the and the decision support system of Merlon. So how the local flexibility manager is structured, starting from a bottom-up approach. Each consumer has an IoT network installed locally, which allows sensing of the indoor ambient conditions, metering of energy consumption, and status monitoring of the devices of interest. And as this communication is bilateral, it also allows control implementation through a local optimization system. All the locally installed devices communicate with an information management layer. So our main focus for this presentation will be actually the information management layer, which provides finally the necessary information and cleans data to the Merlon Local Flexibility Manager. So what the information management layer does is to communicate with all devices locally, translate all the received information in a protocol agnostic manner, clean it, process it, store it, and be able to provide it to the local flexibility manager in order to not only train them building thermal models of each prosumer individually, but also create personalized comfort profiles based on which the local flexibility is finally calculated. So this system is tested in 2 pilots, as mentioned before, that includes the village of Strem in Austria, which addresses 10 households that have implemented relevant loads of PV generation, heating for both domestic hot water and space heating, space cooling, and lights. Also, the prevalent area in Spain involves 11 active residential users, a school, and a local office with loads such as PV and heating in the sense of domestic hot water, as well as lights. Regarding the field equipment, as we are looking at the pilots, the field equipment installed locally includes many different off-the-shelf devices that have different functionalities and include metering or smart control and metering, lighting control, Wi-Fi enabled inverters, multi-sensors, domestic hot water control, and HVAC control as well, all connected and interacting with our gateway based on the Raspberry Pi, hardware. So going upwards to the previously shown architecture, the local devices, and more specifically the gateway, is always connected with the Wi-Fi network and is communicating with the IoT interface within the information management layer. This interface translates in a protocol-agnostic manner all the information collected and transfers it to the IML application layer. So most of the work produced is done within the IML application layer, but before going deeper into that, it's worth mentioning that we have also defined within the IML several common information interfaces that allow the communication of third-party devices or other APIs in order to be able to communicate also with devices not deployed by Hypertech within Merlon. We have already established such APIs, and we are able to have a non-interrupted bilateral communication, both with the locally installed network and with third-party interfaces as well as we speak. So what happens within the IML application layer is that information is collected from all different actors, and there it is processed and handled in order to produce enhanced and cleansed information to be sent directly to the local flexibility manager. Looking closer into the application layer, first of all, regarding the data processing, here is where, as I mentioned, pre-processing, cleansing, and transformation takes place. So what does that mean? Fundamentally, low quality data can lead to badly trained models and, of course, incorrect analysis. What we're trying to do is to produce high quality data without outliers and context aware, and be able to train our models and have high accuracy in our flexibility forecast. All outliers in the collected data are handled without any prior knowledge on the data set we are dealing with, so they are self-trained, and a lot of different methodologies are taken into account depending on the dataset profile in order to be able to more effectively identify these outliers and clean our datasets, while also maintaining the true pattern of the collected information. So here we see such an example where the raw values can be seen in blue. This refers to voltage information, and then we see that after the cleansing, the true pattern of the cleansed values has been revealed, as we see here in orange. The second component of the IML application layer is the data handling component, which overtakes the task of the bilateral communication and information retrieval from the IoT gateway. Additionally, this is the component that verifies that the messages received and stored are actually transmitted from registered and verified devices within the Merlon system. Finally, this is the part, this is the component, the subcomponent that is overtaking one of the most important tasks, which is the device status monitoring, as we have established a continuous monitoring system, which allows us to early define any malfunctions in the system and treat it in time to ensure that we have no data loss and no issues in our communications. So this pretty much summarizes how the IML application works. As I mentioned, this information is introduced for the better training of the profiling, the comfort profiling of individual users and the context-aware flexibility extraction. But due to our time restrictions, I won't be able to go into detail for that. Nevertheless, just to take a quick look on the lessons learned in Merlon. First of all, I can't stretch enough how important data quality is for providing accurate forecasts. For this reason, we have applied cleansing on all data sets collected from all pilot sites, and we are trying continuously to fine-tune our models, to test them, and to train them based on continuously improved data sets. As you understand, collecting all this personal data, of course, is raising concerns about privacy and security. So we are following a fully GDPR compliant methodology in data collection, always trying to keep our data sets anonymized and encrypted to avoid any privacy breach. And looking at the users, user comfort is the most important point in the local flexibility calculation. For this reason, the user perceived comfort is always or should always be preserved through the control automations implemented locally. Therefore, the user comfort model, the user comfort profiles are continuously trained to ensure that any changes due to seasonality or change in users on site will be addressed early on, so these boundaries are not violated. And of course, this contributes immensely to the user acceptance, which is the necessary element for successful DR automations implemented locally. This means that the Merlon tools, as well as the quality of information provided and demonstrated to the users, are continuously upgraded. We are happy to say that at this moment, user acceptance is very high within this project, and we are looking forward to the future results that we are going to receive in the following months while we are testing all the tools discussed. Thank you. Thank you for your attention. If you have any questions, feel free to ask.
Thank you very much, Angelina, for the presentation. So of course, there's going to be some questions, but maybe if we can keep it all at the last section of today's workshop in order to discuss in general. So probably we should continue now with the next presentation on development of an open smart home ecosystem for and by citizen energy communities. Mr. Vincent Dirix will be the presenter from Project VPP.
Hi everybody, I hope you can hear me okay.
Yes, yes.
I will share my screen. Do you see my screen?
Yes, we can see your screen.
This should be better.
Yes, that's great. Thank you.
Okay, so hi everybody. I will present you today the RESCOPE VPP project in which we are developing an open smart home ecosystem for and by citizen energy communities. I don't have to explain you that we have a big shift from a generation that follows the consumption towards the demand that follows a generation. So we have to consume what is available of renewable energies. And in this project, we will focus on how we can do this as communities. We have a big ambition, and that is to create the most advanced community-driven smart building ecosystem. That means it has to be an open ecosystem that communities can join the technology efforts, the developments, and at the end, that also a community layer of organizations, which is RESCOPE EU in this case, will also control the technological developments of overview and organize. So the Horizon 2020 project has, of course, a website, rescopevpp.eu. Here you can find more information. We started in June 2020 with 12 partners and 5 pilot sites. Let me quickly introduce the project parts with SNAP as coordinators. RESCOPE EU as the umbrella organization of citizen energy cooperatives in Europe. Is also responsible for all communication and dissemination, and Energy ID as the technological coordinator. We have some citizen energy communities of cooperatives in our team, a lot actually, Burgerwerken, Carboncoop, Enercoop, Energent, EcoPower, and Som Energia, which are really front-runner cooperatives. These are the biggest citizen energy cooperatives in Europe working together. And we have also Bundesbürger Energie from Germany as an umbrella organization, and 2 universities, the Ghent University and Ljubljana University. We, of course, also are looking into large-scale demonstration, and here are the partners responsible for them in Flanders, EcoPower, Energent, in UK, Carboncoop, Burgerwerken, Germany, Enercoop in France, and Som Energia in Spain. So what are we up to? We look this project from a very practical point of view. It's in innovation action. We want to have real results and real products at the end of the project, which we can bring to the communities. And after, let's say, the first foundational report and foundational work package, we are focusing on 6 targeted services for community. First is about insights. We want people to have personal insights in their consumption, of course, how they manage their capacity or use capacity from the grid, their self-consumption, all kinds of insights that help people to know where they are, their CO2 emissions. This will be an important part. And of course, a community that helps people get their personal insights and understand the personal insights. The second layer, of course, community also wants insight, for instance, on the collective consumption, the collective production, the collective self-consumption. So this is something we want to achieve in a community tools layer. And also important is that the community should also be able to help people with their members, with their personal insights, maybe also for instance, ESCO services. That means a cooperative that wants to help people invest in their homes. Then the cooperative should also be able to look into the personal data for the design purposes, for instance, how big the heat pump should be or the PV installation could be. And then about optimization, the project is about smart homes and legacy equipment. So that means a big part of this project will be enabling local optimizations and make smarter homes at the end. So make sure first there is installations that provide flexibility. That's not the core of the project. Core of the project is when there is flexibility to make sure that there is a coordinated way of enabling smarter homes. The community optimization, with the new EU regulations on citizen and renewable energy communities, it's important that the community itself also could act as an organic group of homes and small buildings and has ways of optimizing itself. So we want to enable smarter communities. We also want to be able as a community to act as a virtual power plant and an aggregation that could sell grid support services to the DSO, to TSO or whatever flexibility market. And the sixth is more of an dissemination, let's say, or after the project, we want to make sure that our products are real products that we can bring to the communities, and we are looking into building together a big European service cooperative to organize all developments and provide the services to the community for all the tools and the products. So the technological overview, what are we talking about? It's 3 levels of control. First is the primary control level, where we look into all the legacy equipments, all of course also new equipments, but we focus on the PV, the heat pumps, the EV chargers, everything that has to do with bigger thermal mass storage, thermal storage, battery storage, electrical batteries, of course, also. And then a level maybe on the smart plugs. Also, white goods are looked into, but we think these are, and based on an EcoSmart Appliances study by Vito, actually, or coordinated by Vito, we look in the main flexibility sources. And so smart plugs is still part of it. Other white goods, we look at more implicit demand response, but I will come into that. The secondary control level, it's what we call, or what we are developing, is a local gateway, the local smart home controller we call the Coffee Box, Community Flexibility Box. It's based on a Raspberry Pi, also based on a big part of working together with Home Assistant, which is one of the biggest open source smart home control systems. And we have a tertiary control level where we connect the smart home controllers to the community, and where the community acts as a gateway to the internet, and where, of course, the community can provide the necessary security for the members, but also provides a secure API for connecting to other third parties to the internet. The Coffee Box itself, it's connected to the home network. It's where we connect with legacy devices. It will connect itself to the Coffee Cloud, where we provide a personal space for personal data. And it's there where we can connect, as I've just said, to further to the internet. It runs blocks of software. Very important is we didn't want to invent the wheel, so we started from Home Assistant, which already provides like 1,800 integrations for all kinds of hardware. So this is where we use this community to make sure we have an easy access to integrations. But also we provide more integrations with digital meters, smart meters, and also we run, of course, all specific blocks of software necessary to make a home a smart home, because this is not provided by Home Assistant. These blocks will be developed using Docker and Python, so Python code and Docker instances, but it's all very known technology, very well known in open source communities. So we try to focus on really available open technologies. This is how the coffee box looks like, where Home Assistant is a part of the basic infrastructure, but we actually decided to make our own common data bus, because we rely on a lot of own blocks of code, and we want to make sure that we are not relying too much on updates of Home Assistants all the time. We talk about some spec integrations, for instance, SG-Ready, Z-Wave, as you can see, digital meters like Fluvius in Flanders, Belgium, but also all the blocks of code on the control strategies. So as we set the secondary control levels, everything that has to do with debug components and databases for data, and then the connection to the tertiary control level. On asset interfacing, of course, this is a major challenge. There is a wide variety of devices, interfaces, installation methods. When a manufacturer provides a very good web API, of course, this is the easiest, but then it requires internet access. The use is not always, sometimes it's locked in a sort of free mode, which is not so interesting on real-time data. For instance, it provides less resolution, it's most of the time not real-time. So it's easy, but not always fast enough, and yeah, the best way to have a local control. So that's why we look in the first place to building communication layers. So in these devices, it's easy and local, but sometimes it requires reverse engineering or a lot of specific implementation. So we want to focus on standards that are well known, but on the level of building communications, we are far from there. So that means that it's an option for us, but we have to really think into the level of the hardware level available in the markets. How many devices of this type are already available? Sometimes cooperatives or communities choose to only choose one or two major manufacturers, and that makes it's also easier. On the third level, we have the physical interfaces. Excuse me. Like SG-Ready, which is just two contacts, which is quite easy, but of course you need relays or some specific dongles or more technical expertise to be able to use them. But in this case, again, we look we look into the real available standards, and then a last option. For instance, if digital meters don't have a local interface to read out, we look at placing real electrical installations like the CT clamps, but that's the last option because, of course, it requires more technical expertise, maybe a local installer. And for us, it's really important that we start from the end user first, and that we actually can just send the coffee box and the user can install as much as possible themselves. For these hardware interfaces, we also implemented a coffee cookie, we call it, concept of small extensions, let's say, on the coffee box, which connect wirelessly with the coffee box. And we talk, for instance, we implemented a digital meter, a smart meter cookie for Flanders, and also it will work in France and in the Netherlands. And this is where the digital meter data can, in seconds resolution, immediately can be transmitted to the coffee box. But also a specific integration for a Wiesmann monoblock heat pump, for instance, in a specific innovation project in Flanders. But this cookie, for instance, would also be developed for the SG Ready interface, which is quite common in a lot of heat pumps. On the level of control strategies, the major control strategy or the interesting strategy for people is their own cost and self-sufficiency strategies. That means increasing self-consumption, make sure that available PV production in the house is optimally used. So based on local data, solar forecasts, optimally scheduling all controllable consumptions. The second one is also individual optimization based on price, so price minimization with dynamic tariffs. That means we make sure that the data of the electricity supplier and the market, that the coffee box is able to get this data easily, and that the local coffee box can use this price to optimize consumption. That means, of course, we need device scheduling, and we look in explicit control on the level of domestic hot water production, on heat pumps, everything that has to do with thermal storage in floor heating or in buffers, electrical batteries, the EV chargers, but also not so important, of course, but an easy case is a smart plug with a specific calendar, for instance, in a kitchen closing boiler. On the other hand, as I said, the white goods, dishwashers, washing machines, dryers, etc., it's more of an implicit control, making sure that the user is well aware of the high cost moments, and that people are able to control themselves the moments they want to use devices. And of course, we look in all the evolutions on EE bus and other standards to communicate directly with smart appliances for the future. On a more advanced level, we look also into minimization of the carbon footprint. So if you go to immediate carbon emissions of the grid electricity, then people could, or the coffee box could also use this to minimize it. Of course, there is less at the moment, which is a pity. Of course, there is a less of an economic value for the user. We should go, of course, to carbon taxation more and make sure that instant carbon value of the grids are more of an economic incentive for people. Another one which is also not at the moment important enough economically is the local grid support on congestion management, voltage control. We have actually already tested our coffee boxes in a previous project where we really followed up the actual voltage in single feeder, and where we have a control strategy to optimize it, but there is not a real market value in this moment with the local DSO. And then on a more advanced level, as I explained in the services, we are looking into its flexibility market participation as a community, which also implicates that local devices should be able to provide explicit demand response for ancillary services and other kinds of flexibility market participation. For this also, we need more community tools, and a very important first step for communities to optimize themselves is, of course, a good forecasting of the demand and the production, and as thus also in the imbalance of the portfolio. So an important use case or a work package in our project led by Enercoop is providing machine learning algorithms for day-ahead forecasts. And this will be also something that our supplier cooperatives in real life can implement for their own business after the project. So this is it for my presentation, I give you here the more information, the project side, of course, the documentation side. Our developments, our Coffeebox will be open sourced. Also, our energy forecasting has its own GitHub repository, and our GitLab group you see. So you're welcome to follow our implementations and try it yourself. Thanks.
Thank you very much for the presentation on risk of the project. We then proceed with the next presentation, which is novel data-driven and service-powered business models for the building sector. The presenter will be John Avramidis, which is the Dissemination Communication Manager from Beyond. So, Yanis, please.
Hello all, let me share my screen.
Then we can see the screen, but if you can put it on the
Okay. Okay, can you hear me?
Yes, yes.
Okay, perfect. Hello all. First of all, once again, let me introduce myself. My name is John Abramidis. I am with UPTech, which is responsible for the development of Beyond's business models and overall for communication and dissemination activities of the project. Today, in the context of this workshop, I'd like to present you our work towards creating data-driven and service-powered business models that they have at their core the building domain. Before we start with the actual work done on the business models, I want to focus a little bit on the environment in which they are to be implemented. As we all know, for many years now, we have been aware that cities not only consume energy, but at the same time produce a huge amount of valuable data due to the introduction of affordable technologies that can be used in every home and offices. But this data, until recently, was not utilized, especially business-wise. Therefore, the question arises whether this unprecedented availability of data can lead energy actors to realize new sources of income by integrating buildings into their business models. In this next slide, my intention is to pinpoint the perspective of how many energy actors conducted their business operations during the past. As you can see here in this figure, and we are probably all very familiar with it, the value chain, energy value chain, was characterized as linear and one way, since energy actors paid, let's say, little attention to their business models. Some of the reasons of this happened were that most of them focused more on tangible products, and on, at the other hand, a highly regulated energy landscape that led to limited, at best, competition. Therefore, energy stakeholders did not invest in innovation and innovative business models, as they were able to cover their costs and realize some profits. But this was about to change, as we'll see. Since during the last 15 to 20 years at least, the energy market has experienced very significant changes. Policy-wise, there were legislations that caused major changes in the energy industry that had to do with the liberalization of the market. And at the same time, the greenhouse effect and the need to reduce CO2, carbon dioxide emissions has also led to regulatory framework for the integration of alternative and distributed energy sources. Technological-wise, the latest developments in big data, AI analytics, and IoT could allow, proved that they could allow the evolution of most business models that hold the promise of growth for the involved stakeholders. Yet, even if many stakeholders have started to invest in such innovations, this is not done in, let's say, a coordinated fashion with the rest of the actors, as these activities target only at this point in time the internal optimization of operations. So, to meet and take advantage of these challenges and opportunities, we at Beyond, we propose the implementation of information and data exchange driven business models based on a data sharing framework that we discussed earlier, enhanced by advanced data analytics that facilitate the transition of energy stakeholders in more extroverted business models. Of course, we are not reinventing the wheel. We are aware of the existence of data-driven smart energy business models, but they are already there, such as home automation, temperature as a service, demand-side management, or even anomaly detection of smart energy systems. So there is a question, what is beyond innovation? According to many experts in the energy domain, they agree on the need for a platform that will facilitate the introduction of new business models, but such a platform shape has not been yet fully defined. To fill this gap, we are developing a data sharing framework with the buildings at each center to meet the requirements of all stakeholders, as we will showcase later in this presentation. To create our business models, we chose to use the value network analysis methodology, which can more effectively reflect data, services, and monetary flows. Another reason for this option was that it is network-centric, also adds the customer as a co-creator of value, and also can include both monetary and non-monetary benefits, making it ideal for the energy sector. So, in this simplified representation of relevant beyond energy value chain that you can see, we can see how it's organized into different factions. These factions are depicting operations and stakeholders, and how this value chain can be enriched, let's say, by beyond services or other technological solutions, as well as building data. Of course, we taking into consideration other factors such as policy, social, and economic variables to conduct these business models. In this slide, we can see how Beyond envisions a value chain that integrates the different actors in the energy landscape with the buildings at the center of this network. It is very easily understood through this image that in this network, different operators can exchange different types of data as well as different types of services that include, as we have seen earlier, both monetary and non-monetary benefits. To make this value network more clear, at this point, I'd like to guide you through the typology of factors and the flows involved. As discussed, we have developed a data-driven business model for the energy value chain stakeholders such as aggregators, network operators, retailers, ESCOs, city authorities, and of course, buildings. In terms of flows, we highlight both data and the flow of services between the various actors, as well as cash flows involved in their realization, indicating the flows that refer to the sharing of data, assets, and services. So, since the goal of today's presentation, my presentation, is not to present all related business model that we have created, but rather to put the rationale supporting them, as well as the role of the Beyond platform that is under development. I will proceed with the description of one of them as an example. So, in residential demand response, the platform plays a central role, as it does in all of our business models, and as it provides data analytics toolkit and can support the installation of other technology enablers and facilitates the sharing of data, sharing of insights, and cash for the data transaction flows. So, in every business model, here is an aggregator assumes the role of the main beneficiary, while others take the role of collaborators as they provide data, and customers as they receive services. For example, on this occasion, an aggregator provides ancillary services and demand response services to network operators and buildings, respectively, and receives back remuneration for those services. One more comment on this slide. Collaborators can be also customers at the same time, as you can see here, and happens with the buildings. Okay, from the realization of this business model can be generated multiple benefits, such as that aggregators are introducing a new service product into the market that has been neglected in current demand response practices and flexibility markets. Also, non-intrusive data-driven flexibility can lead to natural acceptance of demand response residential prosumers. And from the network operator perspective, they could better manage the power in terms of cost through access to cheap flexibility sources by reducing the network's downtime and through the fast responding to critical events, among other benefits. Finally, let me go through some of the obstacles or needs we need to address in order to successfully introduce these business models based on research that we have conducted in the past months, and it's under progress. So this may be related to cultural barriers, as we have found that energy actors are reluctant to share their data as well use external data. Organizationally, there is a lack of staff and systems to deal with relevant data, as well as some privacy and security considerations. To continue with organizational barriers, there is also the fear among energy stakeholders that data sharing could affect their competitive advantage. Finally, with regard to the most technical requirements of the stakeholders, it was suggested that the platform should be scalable, have low operating costs, not jeopardize the performance of the activities carried out, and so minimal complexity. Here is some links to the Beyond social media platforms and the website that you can find more information on not only about the business models, but also about the Beyond project in general. Thank you very much for your attention, and I will be happy to discuss with you if you have any inquiries about the business model in the roundtable.
Thank you, Yanis, very much for the presentation. We should run to the last presentation, which is a roadmap community and a web-based data platform to monitor and transform the European building stock. The presenter will be Philippe Oberegger from BuildHub. So, yes. Hello, Uli.
Hello, welcome to everybody. Can you see my screen?
Yes, thank you.
Okay, so I'm going to present you the Horizon 2020 project BuildHub. This project is about collecting data about the European building stock and its member states for monitoring and transforming ultimately the building stock, and also to develop a roadmap and a community and a web-based data platform for sharing of such data. This project is a coordination and support action. It lasts 4 years, and we are now at the end of our first year. The main roles of our project are to develop a roadmap for sustained data flow to the European Building Stock Observatory. The European Commission is very interested in keeping the observatory updated and to feed regularly data about the European building stock into this observatory in order to develop policies and to inform the public and any stakeholder about the stock. Then we are also going to create and engage a community for data sharing and develop best practices. We will work on standardized data governance and services offered and demonstrated through our web-based platform. And we will coordinate actions among associated projects, and you will see details on the following slides. Visually, the BuildHub project can be summarized as shown here. So we have the platform, and we have several data sets now on the platform, which is in its prototype stage. It is operational since a few weeks, and now it's in an alpha testing phase. On the other hand, we have a community we are building of data providers, users, and beneficiaries in general, and we are, of course, working together with them. We are also working together with the big data projects, Big Matrix and Beyond, and other EU projects. In the end, the overall goal and the mission of BuildHub, endorsed by the Commission, of course, we are in contact with the Commission and other important stakeholders like Eurostat and the Joint Research Center. So the objective is to provide data to an observatory, which will then be available to all stakeholders interested in knowing about the building stock in Europe and developing services for it. So we start with redefining the purpose of the observatory, which is to monitor many kinds of data on the building stock, starting from its characteristics, envelope performance, technical building systems, the energy consumption in buildings, energy performance certificates, economical parameters, the energy market, and also some newer trends like the smartness of buildings, immobility readiness. And of course, we also need auxiliary data to do this, like censuses, cadastres, and climatic data. So we collected already quite some data sets and uploaded them to our platform. And we will work with these data sets to provide services and to develop analytics. So the goal is, of course, also to do quality checks, that was mentioned in previous presentations, to provide high quality metadata, to allow the easy download of data and visualization of data, to do analytics, and to provide also plans and scenarios usable for developing policies or for evaluating renovation strategies. We started with mapping all the stakeholders and data sources and data sets available. We identified quite some barriers, such as data lags, fragmented data, and non-comparable data, privacy issues, also lack of business models. And we therefore want to give recommendations and provide best practices and propose solutions to these to overcome these barriers. And this includes a description of best practices in the data value chain and fair practices. So the data always have to be findable, accessible, interoperable, and reusable, which means to move to the state of the art in technology, but also to use the appropriate business models and to allow data sources to share their data. And this means, for example, to overcome privacy issues, to be to ensure that the intellectual property is preserved, and to have enablers for data sharing, which can go either through an obligation that will be the top-down approach, but even better would be to have enablers and incentives, motivations to share the data. Because in the end, of course, the financial viability needs to be ensured. So we are building and engaging a community through invitations of our stakeholders, and we've done that. We have done also surveys and expert interviews to understand the needs and technical requirements of stakeholders, and many other actions follow, as you can see on this slide. Our community is made of researchers, facility managers, real estate developers, and national and local authorities, etc. We will involve them in testing our web-based data platform and get feedback among them and involve them in thematic discussions. I come to some of the results we obtained in this first year. So we did a survey where we got some contact details of about 80 stakeholders. We have about 50 willing to completely or partially share data with BuildHub. We started, of course, having meetings with them and understand how exactly we can share the data. What we've seen is that they are very much interested in research and analysis of their data, but also in training and education, analysis of future pathways, developing energy efficiency solutions from their data, and to perform environmental decision making. Here you can see an overview of the stakeholders. We have quite a range of countries involved, and we have also a wide range of organization types. A big share is academia, which can be understood easily because they work on such data intensively, but we have also quite an important share of practitioners, professionals, and industry. What we also have seen is what stakeholders would like to have. So data collection is very important, access to more data, basically, but also data analysis and the community building, so the networking with other data holders. And of course, also easy to use visualizations, infographics, and the availability to reuse the data in an easy way. We also did in-depth interviews with experts. We did a bit more than 10 interviews, which are now under analysis. And we will know from these interviews what people consider as benefits of such a platform, what analysis they would like to have, what benefits they would like to have, what they could contribute, etc. We also did quite some networking and outreach in this first year, and we will continue, of course, in the next 3 years. You can see here the logos of some entities we already are working with. We are, as I said, in contact with the big data projects, and we liaise with many other projects. We developed now the prototype of our web-based data platform. Here you can see the architecture. It's quite involved, but I would like to point out that there is the possibility for programmatic access through an API, an application programming interface. There will be a manual access for a general user. You can access through the web or through a browser or through a RESTful API. And there are the services are based on, for now, Amazon Web Services, and the core is a graph database which allows us to use heterogeneous data and to combine different data sets in one database, which can then be queried both for the data and for the metadata. So this platform is very powerful to do data quality analysis, to do analytics, and to provide all the services we will develop. We already combined many data sets into our graph database, and you can see here some of them. We will continue to do so in the upcoming years. The data are mainly building stock related data, socioeconomic data, and climatic data sets. Here you can see a snapshot of our first prototype, which allows then filtering, of course, of the data, visualizing the data, and do the analysis. So stay tuned for further development on this. We have an entry point, a Sparkle entry point for professional users, for advanced users such as software developers. And this will allow, of course, to create external services and to get in an agreement about how to develop further analytics based on the data in the platform. Here on this slide, I wanted to mention that we will also do some estimation of missing data through different kinds of machine learning techniques, such as clustering, for example. And this slide shows that from the data available, like energy performance certificates, billing registers, etc., data can be estimated which is missing. And one of the main issues currently is that there are, of course, gaps both in both geographically, so for some countries, both temporarily for some years in the past, and these gaps can be filled through estimation techniques like the one shown on this slide. With this, I'm coming to an end with my presentation. So if you are interested in getting involved, you can, of course, follow us on our project website. You can easily become proactive, both giving feedback and simply testing out our building data platform. So we look forward to this and to show us what data we have. Of course, as a data provider, so we are always interested in getting more data sets in order to combine them and show what can be done with this data, so we can showcase your data and provide and study with you services and analytics to do with the data. You can also become an ambassador, promoting, as you, of course, are already doing very much in your projects, for responsible data sharing and collection, or just network with us. So you can contact us under the project email address or just write me as I'm coordinating the project. Yeah, with this I finish. So we have an introductory project video which is to be launched in these days, so you can check that out. And we have a brochure, of course, on the project website, which gives some additional information. This is our consortium. We are 8 partners. And with this, I would like to thank you, and I'm, of course, available for any question in the roundtable. Thank you.
Thank you very much, Ulrich Filippi, for the presentation on the Build Hub. Now we have finished all the presentations. We have left like 15 minutes to have an open discussion. So I would like to ask any of the participants if there's a question that needs to be addressed. I know there was a question in the chat. Tassos already have answered it. So please, if there's anybody else regarding the projects, so probably not specifically on the presentation that has been done so far. Tassos, regarding the question that Mr. Arrowsmith has already done in the chat, I don't know if something else that you need to be update or address, something more on that. Yes, Tassos is on the chat that has a sound problem. I thought it was me at the moment.
Hello, thank you very much for me put a question. I hope you can hear me. My name is Greg Arrowsmith, and I'm Secretary General of EUREC, which is one of those organisations mentioned by Ulrich about halfway through his presentation. The next week I have a meeting with some MEPs, and these are MEPs which are very keen to promote digitalisation. They see great opportunity in data sharing, and they are looking for ways to boost data sharing, data access, AI in the Fit for 55 package of the European Commission. One of the elements of that Fit for 55 package is a requirement in the Energy Efficiency Directive for 3% of the floor space of public buildings to be renovated per year from about 2024 to 2030. Do you think that we should be putting an amendment into that legislation that says that we should also be, at the same time as doing this renovation, putting in place systems for acquiring data and putting in place kind of obligatory or at least with very strongly incentivized processes for data sharing? That's a question to anyone on the panel who would like to take it.
Yeah, if I may start, so absolutely. So I think for now there's quite a lack in collecting data or making data accessible, which is being collected. And as an example, if we take the energy performance certificates, there are some countries in which they are easily accessible, and privacy issues and other issues are overcome. As an example, in England, you can, or for England, you can download energy performance certificates, and you have to, of course, agree to the license and to the terms of use, which include that personal data, which is accessible nevertheless, cannot be used in an inappropriate manner. So of course, this must be avoided. But it's possible to get even personal data, and if people don't want to be publicly on the register, they opt out of the program. So of course, an individual can decide to not participate and to not have their data shared. But if they agree, the data is shared and can be used. And while this is quite an extreme stance, where you can look at single buildings and everyone can potentially do this, I think there are ways to aggregate, anonymize, or create synthetic data which can overcome such an issue and make it a little less risky. So by not a too big aggregation and by some anonymization or pseudonymization, or by creating synthetic data, which basically means data which is similar to the real data, but with the same characteristics, data could be shared more easily. And another barrier I see is the motivation to share. So sharing data, preparing data for sharing is very costly, time consuming. And so you need to have the resources to do this. And so how to enable these resources, either it's in exchange of something you get back that you can monetize, or you have the obligation and therefore also the possibility to do such data sharing. I think these mechanisms we should really look into.
Can I also add something in the discussion from my own personal company perspective? So Energy ID is a social finality company with a big platform in Flanders with 40,000 buildings with real data. And we did, for instance, an analysis on 4,000 houses with qualitative data, with PV production, grid offtake injection. With EPC values, we compared with the theoretical values. We have and I really think in this discussion we need to go for real total energy consumptions of houses, and the main goal should be to have a population to compare with, and that is going down on energy need, let's say, the total final energy consumption, for instance, and on the other hand, the CO2 emissions of this consumption. So these two values of real data of a family should be, for me, the basis of any action, because theoretical values in Flanders, for instance, they give an indication, but they don't make any sense in the real CO2 emissions of a household. So if you want to go with data and make sure that policymakers are basing policies on insights, real insights, you need the real energy consumption and the real CO2 emissions, and get people to share it so they can compare it with their population, which is actually for us based on the number of inhabitants in a house, because all the rest is actually not important for the climate. You need the real CO2 emissions of your family. That's it.
Yeah, if I may again, I would just say my opinion on this. So I mean, I agree. The certificates currently are known to be not very accurate, and it's a big discussion how useful they are and how they can be made more useful. And there are some projects, and we are in contact with the consortium working on this, so to make the certificates more useful than they are right now. I would say that the certificates are nevertheless a basis, so it's better than nothing. There's, I mean, a lot of data which, if it's not used, it's worse than the fact that they are not so accurate. But of course, like in the big data projects, big beyond the matrix, where real data is collected and monitoring data is collected, that is, of course, another component which is very important. So in the end, we don't know how the buildings actually behave. It's not so easy to get access to a big and statistically relevant data set, what happens in the buildings. So absolutely, from the monitoring data, collecting and understanding how this can then be brought together is another piece of the puzzle, which is very important.
But I think we don't have to make it too difficult. I think there is a tendency of researchers to make everything much too difficult. In the sense, we connect in Flanders digitally to the digital meters of the DSO. So we have all the daily consumptions of any family when they give us the consent, of course, the GDPR consent. So it's the user that can have its own data accessed easily. The PV installations is also digitally connected. So we have the total final energy consumption of any house, and you need maybe the number of people and the square meters, and then you have an idea of what the final consumption is of a family. And of course, if you want to go to only the energetic quality of a house, then you make it complicated. But of course, you have TV consumption, you have cooking consumptions. Also, it's part of the CO2 emissions of a family is how you live in a house. And we see there are people, families with far less CO2 emissions living in a compact, maybe older house from 100 years old, and they have less consumption and CO2 emissions than any big passive villa built somewhere with the perfect energy quality. You have to look at the total energy consumption of a family, and you need only square meters, number of people, and the digital meter and the PV production in most of the times. And if you start with this easy data source, you can have a perfect benchmark, which we do, and it's not difficult at all. But there should be just a willingness to start from real values instead of some theoretical, far too complex system that at the end only hides the real problem. It's just the total CO2 emissions. You can get an API from your DSO of our regulator, can provide me perfectly with my specific production of my electricity consumption, which power plants were used for my CO2, so the CO2 emissions of my specific contract of my electricity. It's all available, so it's just a few simple API connections and I have my total emissions. And that's the only thing that has to go down, my real CO2 emissions.
So, thank you for everyone for responding to Craig's question. I don't know if Craig, you're okay if you want to ask something more to continue on what already Vincent Ulrich Philippi has answered.
Sorry, was that a question to me, Eleni?
This is the matter covered from your side, from what Vincent and Ulrich Philippi mentioned. if you are covered with the responses.
Oh, sorry. Yes, I am. Yes,
Great.
there was thank you very much. Thanks very much, speakers.
Thank you all. I think that now, unfortunately, it's the end of today's session, of today's workshop. Let's hope we have another workshop, another meeting to discuss more, in order to have more time with an open conversation. I would really like to thank you all for being here today. Hopefully everybody gets to know something more on the rest of the project, especially on the building energy domain. So thank you all for joining today's workshop. Have a nice rest of the day.
Thank you very much.
Thank you very much.
Have a nice evening.
Thank you.
Thank you.
Bye.
Bye.
Bye-bye.